In the second tutorial of section 8.1, we are going to integrate simple functions of the form f of x equal a multiplied by x to the power n, where n is a real number and a is a constant, knowing that n does not equal to -1. Now, let's go back to page 134, where we studied in the first tutorial that if we have dy by dx equal x to the power n, then y equal 1 over n plus 1 multiplied by x to the power n plus 1 plus a constant, and again n does not equal to -1. Knowing that when we have the constant, we call it indefinite integration. Now let's go to example 2, page 135, and try to find when we have a constant multiplied by x to the power n. The first part, find y for the following. We have in part A dy by dx equal to x to the power 3. Then we have a constant a that is equal to 2 multiplied by x to the power 3 that is equivalent to x to the power n. We already know when we have x to the power n, the formula is as follows. So let's take x to the power 3 separately and compare it with x to the power n. Comparing x3 with x to the power n, then n is equal to 3. So n plus 1 is equal to 3 plus 1. Then 3 plus 1 is equal to 4. Therefore, from the formula that we have, if x power n, if dy by dx is x power n, then y equal 1 over n plus 1 multiplied by x to the power n plus 1 plus constant. But in our example, we have 2 multiplied by x power n, then we multiply by 2 as well in y. Therefore, we can substitute now. We have 2, the constant, multiplied by 1 over n plus 1, that is 1 over 4, multiplied by x to the power 4 plus c. Now, 2 multiplied by 1 over 4 is 1 over 2, x to the power 4 plus c. This is y. Then, after integrating dy by dx, we found y equal to 1 over 2, x to the power 4 plus c. If we want to double check, now we can differentiate what we get in the result, 1 over 2 x power 4 plus c, so we can double check if it is the same as the given. Therefore, 1 over 2 stays the same, 4, that is n multiplied by x, and we reduce 1 from the power. The derivation or the differentiation for the constant is 0. This is equal, half multiplied by 4 is 2, and x to the power 3, which is the same as the given. Then our solution that we did is correct. Whenever we have a constant multiplied by x to the power n, then in the integration we multiply by this constant. In part B, we have dy by dx equal 3 multiplied by x to the power 1 over 2. Then we have a constant 3 multiplied by x to the power n, that is x to the power half. Therefore, n equal half, n plus 1 equal half plus 1 equal to 3 over 2. Therefore, substituting in y, it means that 1 over n plus 1 x to the power n plus 1 plus constant, and we have to remember to multiply by 3 the constant. So we multiply x by the constant. Therefore, we get 3 multiplied by 1 over 3 over 2 x to the power n minus 1, that is 3 over 2 plus the constant, equal, now 3 stays the same, multiplied by 1 over 3 over 2, the reciprocal is 2 over 3, then it's 3 multiplied by 2 over 3 multiplied by x to the power 3 over 2 plus the constant. This is equal, by cancellation, 2x to the power 3 over 2 plus the constant. As you can see, now we use derivation to be able, or integration, to be able to find y from dy by dx, where xn in these two applications is multiplied by a constant. Then in the formula we multiplied as well by the same constant, and we treated all the expression in the same way. So notice that you treat dy by dx equal x to the power n and dy by dx equal k, a constant multiplied by x to the power n, in the same way. You only consider the x power n term when integrating. If dy by dx equal k x n, then y equal kx to the power n plus 1 divided by n plus 1 plus constant where n does not equal to minus 1.